Today we're going to talk about digital image fundamentals. The topics we're going to talk include image acquisition and formation, resolution and size of objects, spatial sampling and quantization, and then do some MATLAB exercises. So the objectives is to learn how to estimate properties of image acquisition and formation, such as the resolution and size of objects that can be discerned, and be familiar with the effects of spatial sampling and quantization on the quality of an image and its storage size. First, let's just take a look at an example of a imaging system. This is the human eye, not a digital system, of course, but it's a working example of how such a system works. So the human eye has a lens. Light comes in through the cornea. It's refracted partially through the cornea and then focused additionally through the lens, and then is focused on the retina over here, which is actually a spherical image surface. So the retina is covered with rods and cones, which are light-sensitive cells. The fovea is the densest portion of the retina in terms of cones. So it's about 1.5 millimeters in width and contains about 337,000 cones. The distance from the lens to the retina is about 17 millimeters, so that we take as the focal length of the eye. This shows the density of rods and cones as you get away from the fovea, which is at 0 degrees. So remarkably, you can actually see out to about 80 degrees in either direction. But the size of the fovea, of course, is just the very narrow part around 0 degrees. So the cones are primarily in the fovea. The rods are distributed in the outside away from the fovea. Let's look at how we can predict image formation. So here's, let's say, a human eye, and we want to, let's say, estimate how big an object would be projected on the retina here. So for the rest of the course, we're going to treat cameras as a pinhole camera. What that means is you have a very narrow pinhole aperture through which light passes undeflected, and is the rays just project directly onto the image plane here. So this is an easy way to predict size of objects because we can use similar triangles. Namely, the height of the object, the ratio of that to the distance is the same as the height on the image plane compared to the focal length f here. So for example, in this case, we have a tree that is 15 millimeters high. It's 100 meters away. The focal length is 17 millimeters. We want to predict the height h on the retina. Notice that the image is actually inverted here, but we can easily switch that around. So using similar triangles, we have big H divided by d, which is the distance, is equal to small h divided by the focal length f. So in that case, the height on the image plane would be 2.55 millimeters. If the tree were twice as far away, the size on the image plane would be half if you just look at the equation here. Interestingly, though, if the tree was twice as far away but twice as big, you would get the exact same image. Let's look at this problem from the textbook. They say, let's assume the retina is 337,000 sensor elements that's on the fovea, arranged in a square array of 1.5 by 1.5 millimeters. And the space between the cones is equal to the width of the cones. So we want to estimate the diameter of the smallest printed dot that the eye can see if the page is 0.2 meters away from the eye. And we're going to assume that the visual system ceases to detect the dot if the image of the dot is smaller than the diameter of one cone. Okay, so let's draw this. Here is our fovea, and it contains an array of cones. And it is 1.5 millimeters by 1.5 millimeters. And the spacing, I'll call it little, well, the width, the diameter of a cone is equal to the spacing between the cones. Okay, so to predict the size on the image plane, let's draw that. So let's say we have our image plane here. Here's our focal length f. Here's the dot. Okay, so the dot has some unknown height h. We know the distance is 0.2 meters, and the dot projects onto the image plane, creating an image of the dot of height little h. Okay, so we know f. That's the focal length of the eyeball. We know d. We don't know h, and we don't know big H. We can find out little h from the dimensions of the fovea, though. So we know that the fovea has, it's a square array, n by n, which is 337,000 cones. So n is the square root of that, which is about 580. So I have 580 cones plus 580 spaces between the cones in a dimension of 1.5 millimeters. So one cone has a diameter, call it little h, equal to 5 divided by 580 plus 580. It's 1.3 times 10 to the minus 6th meters. I guess I have that in meters here. Okay, so that gives us little h here, which is 1.3 times 10 to the minus 6 meters. Okay, so now we can use our similar triangles to calculate what big H is. Using big H over D, that's the same as little h over F, or big H is equal to D H over F. And that comes out to be 15.3 times 10 to the minus 6th meters, or converting that to millimeters, 0.15 millimeters. Okay, so that's the minimum size of a dot on a page that would be 0.2 meters away from your eye.